So with a weaker electric field, the potential between the plates is smaller. If we come down to this result here, if we have a smaller potential without actually changing the physical charge on the plates, if this is the same and this is smaller, what must happen to the capacitor? The capacitance? The capacitance must increase. So the effective result of having a material in here is to increase the capacitance of the capacitor. I'm going to rewrite this equation with a new quantity C without the subscript O. We'll use this for the capacitance of the capacitor when it's filled with a material. And this material, whatever we put in here, that's either got a dipole moment or can have an induced dipole moment, this type of material is what we call a dielectric. So our capacitor that is filled with a dielectric has a new capacitance that we'll write as capital C, and then I'll rewrite this equation with the quantities Q and V without the subscript O to indicate that these are the quantities that are the charge, the capacitance, and the voltage across the filled capacitor, the dielectric filled capacitor. So we've got these two equations. They look very, very similar to each other, but keep in mind that the subscript O means a vacuum-filled capacitor, and with no subscript, that is a dielectric-filled capacitor. Now, what happens? How do we go from the vacuum-filled capacitance to the dielectric-filled capacitance? Well, this increases, and the amount that it increases depends on the material that we put in it, the dielectric. Different dielectrics will increase the capacitance by a different amount, depending on how much a dipole moment the material has. So we have a relationship that our new capacitance is equal to our old capacitance, but increased by a factor that we'll write as a lowercase Greek letter kappa. So this is called, this is a lowercase Greek letter kappa, and kappa is what we will call the dielectric constant for the material that we put in there. Different quantities will have different dielectric constants for so different materials have different values of dielectric constant. Just as an example, water, kappa for water, is 80.4, which is actually a rather large dielectric constant. It increases the capacitance of the capacitor quite a bit. Okay, let's stick some numbers in here. What is the voltage required to store, let's say, 3 microcoulombs on a, oops, and I just realized I forgot something. Let's go back to our equation, Q equals CV. What are the units of capacitance? So the units of capacitance, if we write QC equals Q over V, the units of capacitance will be the units of Q over the units of V. So what are the SI units of Q that we've been using? Those are coulombs. So that's a coulomb. And the units of voltage, well, that's a volt. Now this combination of units is something that we're going to see over and over again, and so it's actually got its own name, like so many of these units do. 1 coulomb per volt is called a farad. And the symbol that we'll use for a farad is a capital letter F. So the units of capacitance are farads. Now, just as an aside, let's think about this. Why is it called the capacitance? Well, I'll give you a little bit of an idea. If I were to ask you, if I had a bucket and I said the capacity of this bucket is 5 gallons or something like that, what does that mean? Excuse me. It means that the bucket can hold 5 gallons of water or whatever. The capacity tells us how much the bucket can hold. Well, what do we mean by the capacitance of a capacitor? Well, let's imagine that we had a capacitor with a capacitance of, let's say, 5 farads. Well, if we put a voltage of 1 volt across the capacitor, what would the charge be? The charge would be C times V, 5 farads times 1 volt, that would be 5 coulombs. So the capacitor would hold 5 coulombs for a voltage of 1 volt. What if the capacitance were 6 farads? Well, then we would have a charge of 6 coulombs. 10 farads, 10 coulombs. So the capacitance tells us how much charge the capacitor can hold per volt. So if we actually doubled the voltage, if we had 2 volts and 5 farads, then we'd hold 10 coulombs. So the idea is that the capacitance tells us how much charge the capacitor can hold per volt. That's kind of the idea, capacitance, capacity. Okay, so back to our problem. What is the voltage required to store 3 microcoulombs on, let's say, a 7 picofarad capacitor? And let's assume at this point it's vacuum filled. Well, we've got the voltage, we've got, what is this? This would be the charge. And let's assume this is vacuum filled, so I'll call that Q naught. If it's vacuum filled, this will be C naught. And so what is the voltage? So we're actually looking for V naught to start with. What's the relationship here? We know Q naught equals C naught V naught. So V naught is equal to Q naught divided by C naught, or let's put all these in standard SI form. We've got 3 micro, 10 to the minus 6 coulombs, divided by C naught, 7 picofarads. Now, pico, remember, is not one of the prefixes that I expect you to memorize, the ones that I want you to memorize in the beginning of the semester that I told you about. Pico is minus 12 farads, so we divide that out, and what do we find? V naught is equal to 4.29 times 10 to the 5th volts. Okay, that's a lot of volts. That's a very high voltage. That's basically a lot of charge for a little tiny capacitor. Now let's imagine we take this capacitor and let's fill it with water. Imagine it's big enough that we could actually get some water in there. So let's figure out what is our new voltage. Let's assume that we keep the same charge. Well, if we keep the same charge, that's also going to be Q, not just Q naught. What's our new capacitance? Well, the new capacitance, remember, is kappa times the vacuum-filled capacitance. And assuming we fill this with water, okay, remember the dielectric constant of water is 80.4. So times the vacuum-filled capacitance, which is 7 picofarads. Our new water-filled capacitance is 5.63 times 10 to the minus 10th farads. And what's our new voltage? The new voltage will be equal to the new charge over the new capacitance. The new charge, same as the old charge, 3 times 10 to the minus 6 coulombs divided by 5.63 times 10 to the minus 10 farads. Divide that out and we find the new voltage is 5.33 times 10 to the 3 volts. We notice it is less than the old voltage, and actually it's less by a factor of 80.4, the same as the dielectric constant of the water. Okay? There we go. Now, one more thing I want to mention. How much energy is actually stored on a capacitor? So let's imagine we've got a capacitor, 2 plates, but initially uncharged. There's no charge on it. what I want to figure out is how much energy, how much potential energy have we actually stored on this once we get it charged up with some positive Q and negative Q charge on it. Let's assume that it's got some capacitance, C, to begin with. Now, in order to calculate this really exactly, we could do this very, very easily using a little calculus, but we don't use calculus in 1112, so we're going to do it a little back of the envelope, little simplified idea. So what we want to do is we want to get some large charge on this with minus Q and plus Q on the two plates. But how are we going to do that? We're going to do that step by step. We're going to start out by moving, let's imagine like one little proton, one little charge of plus Q. We're going to take off one plate and move it over to the other plate. So we're going to make an initial charge of minus Q on one plate and plus Q, a little tiny little Q on the other plate. Now to begin with, the voltage difference between the plates will be 0. When there is no charge on the plates, the initial voltage will be 0. After we've completely charged up the plates, we'll have some final voltage of V where we know Q equals CV. Once we get the entire charge Q, we know we'll have a voltage across the plates of V once it's completely charged. So the idea is, as we move one little Q and then another little Q and another Q and another little Q and another little Q, the potential builds up from 0 to its final value. Well, on average, we might imagine then that the potential we have to work against is 1/2 the final value. Okay, does that make sense? That first little Q has to go against 0 force, so it takes no work basically to move that first little Q. That final little Q has to go against the entire voltage, so we start out with a change in potential energy of that first little Q of 0. The final change in potential energy of that last little Q will be that little Q times the entire voltage. On average, we're going to be working against 1/2 the final voltage. Okay, if that doesn't make sense, don't worry about it. The bottom line is the final result is that the potential energy of the entire work that we had to do is 1/2 that final voltage times the entire charge. So moving little bits of charge one at a time is essentially moving it on average against 1/2 the final voltage. And so this is what the final potential energy is, the final energy stored on the capacitor, 1/2 V times Q, or 1/2 QV. Well, if we know that Q is C times V, we could put C times V in for Q, and we could write this as 1/2 CV squared. Or if we write V as Q over C, we could write this as 1/2 Q squared over C. And there we've got 3 different forms for the energy of the capacitor: 1/2 QV, 1/2 CV squared, 1/2 Q squared over C. Any of those will work to determine how much energy is actually stored on the capacitor. I don't expect you to remember the dielectric constant of water, but there is one value of a dielectric constant that I do expect you to remember, and that is the dielectric constant for air. For air, the dielectric constant is 1.00. Now, it is actually a little bit larger than 1, but it's only larger than 1 over on some of these other decimal places. So, to 3 significant figures, the dielectric constant for air is 1.00. Okay? Okay, that's all for now. You're going to use these on the homework, give those a try, and I'll see you next time.